There is a moment before every story begins, a blank page before the first word, a silence before the first note. But what about the story of everything? What existed before the cosmos itself flickered into being? This is the ultimate blank page, the profound mystery of what came before the Big Bang. By the end of this journey, you will explore the leading scientific theories that attempt to answer this question, transforming cosmic philosophy into tangible, mind-expanding ideas. We will venture into realms where time loops back on itself, where our universe is just one bubble in an infinite foam, and where the very concept of a beginning dissolves into quantum possibility. What does your intuition whisper about the moment before creation? Our story must start with the moment we think we understand, the Big Bang. It has become a cultural shorthand for the beginning of everything, but the scientific reality is far more subtle and far stranger than a simple cosmic detonation. Picture not an explosion in space, but the explosive expansion of space itself. The entire observable universe, every galaxy, every star, every atom, was once compressed into a region of unimaginable density and temperature, smaller than a single atom. Then space began to stretch and cool at a phenomenal rate. We see the echoes of this event all around us. The faint afterglow of that primordial heat bath, the cosmic microwave background radiation, fills the entire sky. We see galaxies racing away from us, their light stretched into longer, redder wavelengths, telling us the fabric of the cosmos is still expanding. This is the powerful, evidence-backed story of our universe's evolution from that hot, dense state. But here is the crucial, haunting detail the model leaves blank. The equations of the Big Bang take us back and back and back to a point of infinite density and temperature, a singularity. At that point, our best laws of physics simply break down. They cannot describe it. So while the Big Bang tells us with great confidence what happened immediately after the beginning, it is completely silent on what caused that beginning, or what, if anything, existed before the clock started ticking. The starting gun fired, but who or what was holding it? This silence is the doorway to our mystery. This singularity is not just an extreme condition, it is a mathematical dead end. Think of it like trying to divide a number by zero. Your calculator flashes an error because the operation is meaningless within its rules. The equations of Einstein's general relativity, which so beautifully describe the curvature of space-time by mass and energy, perform a similar error when they are wound all the way back to time zero. They predict a point of infinite density, infinite temperature, and infinite curvature. In physics, infinity is almost always a red flag. It is not a description of a real place, but a glaring sign that our theory has hit its limits, that we are asking it a question it was never built to answer. The singularity is not a thing, but a boundary, a blank wall in our understanding. It tells us that the physics we use to describe the universe today, as vast and mature as it is, cannot describe its own birth. So when we ask what came before the Big Bang, we are not merely asking about an earlier moment in time. We are asking what laws, what reality, existed in a realm where our familiar concepts of time and space, of cause and effect, simply do not apply. The quest to peer before the beginning is therefore a quest for a deeper theory, one that can replace that error message with a true first chapter. One compelling answer to that blank wall is to erase it entirely. What if the Big Bang was not a beginning but a transition? This is the heart of the cyclic universe model, a vision of cosmic history with no true start and no final end. In this story, our universe is caught in an eternal rhythm, a grand cosmic heartbeat of expansion and contraction. The cycle begins with a universe much like our own, filled with galaxies and stars. Over eons, the expansion slows, halts, and reverses. Everything begins to fall back together in a great inward rush known as the Big Crunch. All matter and energy are compressed once more toward a point of incredible density. But instead of hitting a dead-end singularity, something remarkable happens. At the very peak of that compression, the laws of quantum gravity, which govern reality at the smallest scales, take over. They prevent a true infinity from forming. Space-time at this level is not a smooth continuum but a seething, granular quantum foam. This structure provides a kind of cosmic resilience, a repulsive force so powerful that it reverses the collapse. The universe bounces. That rebound is what we call the Big Bang, the start of a new cycle of expansion, cooling, and eventual life. In this view, our entire cosmic history is just one beat in an endless rhythm, with an infinite past of previous universes and an infinite future of ones to come. Our world emerged not from nothing, but from the ashes of a previous cosmic era, which itself was born from one before it, in a chain stretching forever backward and forward. This elegant idea transforms the mystery of the beginning into a question of eternal return. What echoes from the previous universe might linger in our own? Could the faint patterns in the cosmic microwave background be the ghostly imprint of a cosmos that came before? But what if the bounce is not the only escape from the singularity? Another profound idea suggests our universe did not emerge from a prior state of matter, but from a prior state of space itself. This is the theory of eternal inflation, and it paints a picture far more vast and strange than a simple cycle. It begins with a concept you may have heard of: cosmic inflation. Most cosmologists agree that a fraction of a second after the Big Bang, the universe underwent a breathtaking growth spurt, expanding faster than the speed of light, smoothing itself out and planting the seeds for galaxies. But what if that inflationary period was not a one-time event? What if it is the default, eternal state of a deeper reality? Imagine a vast, roiling ocean of pure, hyper-energetic space-time, a meta-universe called the inflatoned field. In this seething quantum sea, inflation is always happening, stretching this primordial fabric exponentially and forever. But like a pot of water coming to a boil, this eternal inflation is not perfectly uniform. Tiny quantum fluctuations can cause pockets of this hyper-expanding field to suddenly lose energy, to cool and settle down. When that happens, inflation stops inside that local region. The enormous energy that was driving the expansion is released, flooding that pocket with light and matter, igniting a hot Big Bang. That pocket becomes a universe like ours, with its own laws of physics, its own stars, and potentially its own life. And here is the breathtaking part. While that pocket universe forms and evolves, the eternal inflationary ocean outside it continues to expand furiously, and within that endless ocean, more quantum fluctuations are constantly spawning new bubbles, new universes, each with its own unique Big Bang moment. In this view, our entire cosmos is just one bubble in an infinite, ever-expanding foam of universes, a multiverse. So what came before our Big Bang? In a linear sense, there may be no single answer. Our universe is not a chapter in a sequential book, but a branch on an infinite, ever-growing tree. The inflating meta-universe has always existed, endlessly giving birth to new cosmic islands. The question of a beginning dissolves into a landscape of eternal creation, where beginnings are happening everywhere, all the time. But a bubble universe or a cosmic bounce still assumes a framework of space and time. What if that framework itself is an illusion, a grand cosmic mirage? This brings us to perhaps the most radical reimagining of all, the holographic principle. It proposes a staggering possibility. Our rich, three-dimensional reality, with its galaxies, planets, and people, might be nothing more than a magnificent projection. A cosmic movie, if you will, whose data is stored on a distant, two-dimensional screen. The origins of this idea come from the most extreme environments we know of, black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume, as you might expect for a three-dimensional object. Instead, it is precisely proportional to the surface area of its event horizon, the two-dimensional boundary from which nothing can escape. This was a profound clue. It suggested that all the information needed to describe everything that falls into a black hole is somehow encoded on its surface like a cosmic DVD. The three-dimensional interior is projected from the data on its two-dimensional boundary. Extend this wild logic to the entire cosmos. The holographic principle suggests that our universe in its entirety could be a similar projection. The three spatial dimensions we experience, along with time, may not be fundamental. They could emerge from a vast, complex network of quantum information stored on a remote two-dimensional surface that encloses our reality. So what does this mean for the Big Bang? In this view, the Big Bang might not be the explosion of a three-dimensional point, but the moment this cosmic projector switched on. It marks the instant when the information on that primordial two-dimensional surface began to be translated or decoded into the three-dimensional universe we inhabit. The question of what came before the Big Bang then undergoes a fundamental shift. It is no longer about an earlier moment in time within our three-dimensional experience. Instead, it becomes a question about the prior state of the information on that boundary surface. Did that information exist in a different form, perhaps as a quantum fluctuation in a deeper, more abstract realm? Was it rearranged, or did it simply begin to be processed in a new way? The holographic principle transforms the mystery of cosmic origins into a puzzle about data and its translation. Before our universe, there may have been no where or when as we know them, only a potential for information waiting to be rendered into the spectacular, tangible reality we now call home. Yet another vision of cosmic rebirth completely redefines the idea of a cycle. This is Roger Penrose's theory of conformal cyclic cosmology, a proposal so elegant and strange it suggests our universe has no distinct beginning or end at all, but is instead one link in an infinite chain of eons. In this radical picture, there is no dramatic big crunch, no violent bounce, and not even a singularity to mark a boundary. Instead, the transition from one cosmic era to the next is a smooth, almost peaceful transformation, a fading out and a fading in. To understand how this is possible, we must look to the very far future of our own universe, trillions upon trillions of years from now. In that unimaginably distant time, the expansion of space will have carried all galaxies beyond the cosmic horizon. Stars will have burned out, and black holes will have slowly evaporated through Hawking radiation. What remains is a universe cold, dark, and almost perfectly empty, populated only by the faintest of entities, massless particles like photons or light particles, drifting endlessly through an ever-expanding void. In this state, the universe has lost all sense of scale. With no massive objects left to provide a reference point, the concepts of distance and time become meaningless. A single photon traveling across this vast emptiness experiences no passage of time at all. This featureless, timeless state is the key. Penrose proposes that this distant future of one eon can be mathematically connected to the hot, dense, low-entropy beginning of the next through a process called conformal rescaling. Think of it like this. Imagine you have a detailed map of an entire continent. Now you take that map and smoothly shrink it down, not by crumpling it, but by perfectly adjusting all its proportions until it becomes a map of a single city. The information is preserved, but the scale has changed completely. In conformal rescaling, the infinite expansion and cooling of the old eon is mathematically transformed into the hot, concentrated burst of the new one. The endless, cold future becomes the hot, dense beginning. There is no singularity because the point of transition is not a point of infinite anything. It is a boundary of scale where physics becomes simple and symmetrical. So in this view, our Big Bang was not an explosion from nothing, but the conformally rescaled aftermath of a previous universe's eternity of decay. And the eventual fate of our own cosmos, that cold, empty drift, will itself become the fiery dawn of a brand new eon, with its own galaxies, stars, and perhaps its own curious minds asking the very same question. The universe does not bang or bounce, it simply forgets its size and starts the story over again, in an endless, majestic loop without a true edge. Yet even the holographic principle and Penrose's cycles operate within a framework that assumes certain laws of physics. But what if the laws themselves are not fixed, not fundamental truths written in stone, but merely local bylaws, accidents of cosmic geography? This is where our quest leads us into the deepest theoretical waters, to string theory and its staggering implications. To understand this, we must first grasp a core idea of the theory. It proposes that the fundamental building blocks of reality are not point-like particles, but incredibly tiny, vibrating loops of energy, strings. And for the mathematics of these strings to work, they require more dimensions than the 3 of space and 1 of time we experience. They require a total of 10 or 11 dimensions. So where are these extra dimensions? The theory suggests they are curled up or compactified on a scale so vanishingly small that we could never perceive them directly. Now here is where the cosmic lottery begins. The way these extra dimensions curl and twist upon themselves is not unique. There are, according to the math, a colossal number of possible stable configurations, perhaps 10 to the power of 500 different ways. Each distinct configuration of these hidden dimensions determines the effective laws of physics in the larger, observable universe. The strength of gravity, the masses of electrons and quarks, the number of fundamental forces, all of these become consequences of the specific geometric shape of the compactified dimensions. In one specific configuration, you get a universe like ours with carbon atoms and stable stars. In another, you get a universe where atoms cannot form, or where gravity is so strong that any star instantly collapses. This vast collection of every possible stable configuration is called the string theory landscape. Now connect this to the idea of eternal inflation. Remember that seething, hyper-expanding ocean of space-time, the inflatoned field. In this framework, each quantum fluctuation that forms a new bubble universe is not just creating a new region of space. It is also randomly selecting a point on this unimaginably vast landscape. As that bubble inflates and cools into its own Big Bang, the extra dimensions within it settle into one specific, stable configuration. That configuration then locks in the laws of physics for that entire universe. Our universe, with its particular constants and forces, is simply the result of one random roll of the cosmic dice in one particular bubble. This transforms our understanding of before. Before our Big Bang, there was no single linear timeline leading to our specific laws. Instead, there was and is a chaotic, higher-dimensional process of eternal inflation, endlessly churning out bubble universes, each one a random sample from the near-infinite menu of the string landscape. Our existence is not the predetermined goal of creation, but a fortunate accident in a multiverse of endless experimentation, where most bubbles are sterile voids or chaotic fires, and only a rare few, by pure chance, have the right recipe for complexity, for stars, and for life. Yet with all these visions of cycles and multiverses, a fundamental question lingers. Must there be a prior something, a pre-existing canvas for our universe to be painted upon? What if the canvas itself is part of the painting? This brings us to one of the most elegant and profound attempts to answer that question, the no-boundary proposal by Stephen Hawking and James Hartle. It is a model that does not just sidestep the singularity, it erases the very idea of a boundary to the universe altogether. To grasp this, think of our planet. You can travel across the surface of the Earth forever in any direction, and you will never find an edge, a precipice where the world simply stops. The Earth is finite, yet it has no boundary. Hawking and Hartle asked if the same could be true for the universe in time. Could the cosmos be finite in its history, yet have no sharp, singular beginning, no moment of creation where the laws of physics break down? Their ingenious answer uses a concept from quantum mechanics called imaginary time. Do not let the name confuse you. Imaginary time is not make-believe time. It is a mathematical tool, a different way of measuring the dimension of time that allows for a smooth, continuous description of reality at the very smallest scales where classical physics fails. In this framework, when we trace the history of the universe back toward the Big Bang, something remarkable happens. The usual, familiar arrow of real time, the one that flows from past to future, becomes fuzzy. It blends and transforms, much like how the lines of longitude on a globe converge at the North Pole. At that point of convergence, time behaves not like time at all, but like another dimension of space. This is the heart of the proposal. The Big Bang is not a wall, not an explosion from a point. It is more like the North Pole on our globe. If you stand at the North Pole, the concept of going further north ceases to have meaning. Every direction you look is south. In the no-boundary universe, asking what happened before the Big Bang is like asking what lies north of the North Pole. The question loses its meaning because the framework of a linear timeline simply does not apply there. The universe in this model does not have a moment of creation in time. Instead, it has a shape in a blended reality of space and imaginary time, a smooth, closed surface without any sharp edges or tearing seams. So how does the universe come to be? From this seamless geometry, Hawking and Hartle suggested it could emerge as a spontaneous quantum fluctuation. In the quantum realm, empty space is not truly empty. It seethes with potential, with virtual particles popping in and out of existence on borrowed energy. The no-boundary proposal extends this idea to the entirety of reality. The universe itself could be the ultimate quantum fluctuation, not appearing in a pre-existing void, but bringing space and time into existence along with it. There is no before because there is no time for a before to exist in. There is simply the self-contained, finite, and unbounded reality of the cosmos simply being. It is a vision that trades the mystery of a first cause for the deeper mystery of a self-contained, self-originating existence, a universe that needs no external starter because in its most fundamental description, it never had an edge to start from. The no-boundary proposal offers a breathtaking vision of a self-contained cosmos, but it is not the only quantum path to our beginning. Another radical idea from the depths of string theory completely inverts the classic story we think we know. This is the pre-Big Bang scenario, and it suggests our universe did not start in fire but in ice. Picture this not as an explosion from a point of infinite heat, but as a great cosmic thaw. In this model, the universe we call home began in a state of profound stillness and cold, a vast, nearly empty expanse that was slowly, gravitationally contracting. This was a pre-Big Bang era governed by the principles of quantum gravity as described by string theory. In this cold, contracting phase, the universe was incredibly large and incredibly dilute. Matter was sparse, temperatures were near absolute zero, and everything was drawing inward. But as space contracted and densities began to rise, the universe approached a kind of quantum barrier, a point where the known laws of physics would break down. Yet, according to this scenario, they do not break into a singularity. Instead, the universe undergoes a dramatic phase transition. Think of water. Cool it down slowly and steadily, and it remains a liquid until at a specific critical point, it transforms into solid ice. The pre-Big Bang scenario proposes a similar cosmic flip. When the contracting universe reaches a state of maximum but finite curvature and density, it does not collapse into nothingness. The unique physics of strings and quantum gravity cause it to rebound, not with a bounce into more cold contraction, but with a fundamental transformation of its very state. That moment of transition is the Big Bang. In an instant, the cold, contracting, low-entropy universe transforms into a hot, expanding, high-entropy one. The energy bound up in the fabric of space itself is released in a flash, flooding the newborn cosmos with radiation and matter, setting off the expansion we still observe today. It is a complete narrative inversion. We emerged not from a hot, dense point, but from a cold, dilute expanse that passed through a looking glass and came out as something utterly new. The fiery dawn of our cosmos was, in this story, the aftermath of a great freeze. This elegant idea solves several theoretical puzzles at once. It provides a natural explanation for why our early universe was so remarkably smooth and uniform, a condition the classic Big Bang model simply assumes. In the long, slow contraction of the pre-Big Bang phase, any irregularities or wrinkles in space-time would have had ample time to be stretched out and smoothed away, leaving a pristine canvas for the hot Big Bang to paint upon. Yet for all its theoretical beauty, the pre-Big Bang scenario faces the same monumental challenge as all ideas about the ultimate beginning. How do we test it? The event itself is shrouded in the opaque physics of the quantum gravity epoch, a realm our telescopes cannot directly see. Scientists look for potential echoes, subtle imprints that the pre-Big Bang contraction might have left on the universe we can observe. One key signature would be a specific pattern of gravitational waves, ripples in space-time from that primordial transition that might be detectable in the polarization of the cosmic microwave background. Another might be a faint, statistical oddity in the distribution of the very first galaxies. Finding such a fingerprint would be like discovering a fossil from a world that existed before our own world was born. It remains a profound and compelling what-if, a reminder that our origin story may be far stranger and far more serene than the explosive birth we have always imagined. These invisible forces that sculpt our universe today may be its oldest inhabitants. While we chase the ghost of a beginning, we are surrounded by profound mysteries that govern the present, mysteries whose origins might be written in that first moment. Dark matter and dark energy are not just gaps in our knowledge, they are the dominant architects of cosmic reality, and they could be the living fossils of the pre-Big Bang era. Let us start with dark matter, the universe's hidden skeleton. We cannot see it, touch it, or detect it with any telescope that reads light, yet we know it is there. Its immense gravitational pull is the only thing that explains why galaxies spin as fast as they do without flying apart, and why immense clusters of galaxies hold together. It is the cosmic glue that drew ordinary matter into the vast webs and filaments we see across the sky. But what is it? We do not know. The leading candidates are exotic, slow-moving particles that barely interact with light or ordinary matter, relics from a time of unimaginable energy. And this is where the connection to origins becomes tantalizing. Could dark matter be a remnant from before our cosmic cycle began? In models like conformal cyclic cosmology, where one eon gives birth to the next, information must somehow be preserved across the boundary. The peculiar, stable particles that constitute dark matter could be survivors of that transition, entities that somehow navigated the conformal rescaling from the old, cold universe into the fiery dawn of our own. They would be cosmic immigrants carrying with them the faintest imprint of a world that existed before time as we know it began. Similarly, in a bouncing universe model, the violent crunch and rebound could have forged these particles in abundance, leaving them as a permanent gravitational echo of the bounce itself. Dark matter, then, might not just shape galaxies, it might be the physical memory of the universe's own birth trauma. Then there is dark energy, an even more enigmatic force. It is not matter at all, but a property of space itself, a kind of anti-gravity causing the expansion of the universe to accelerate. Discovered only in the late 1990s, dark energy is the dominant component of the cosmos, and we understand it even less than dark matter. One compelling idea links it directly to the story of cosmic beginnings. Recall the theory of eternal inflation, that seething, hyper-expanding ocean of space-time from which our bubble universe emerged. That inflationary drive was powered by a specific energy field, the inflaton field. When our pocket of space cooled and settled, that inflation stopped here, releasing its energy to create our hot Big Bang. But what if it did not stop completely? What if a tiny remnant of that inflationary energy lingered, woven into the very fabric of space? This faint, persistent energy, repulsive in nature, could be what we now call dark energy. In this view, dark energy is not a new actor on the cosmic stage. It is the dying ember of the fire that started it all, a direct link to the mechanism of our creation. It is the afterglow of Genesis, still pushing the universe apart long after the initial explosion has faded. Connecting these present-day mysteries to the ultimate unknown transforms our quest. We are no longer just looking backward through time with telescopes, trying to see a beginning we can never directly witness. We are also looking around at the universe we inhabit, studying the behavior of dark matter and the push of dark energy, searching for clues in their properties. The specific way dark matter clumps or the precise strength of dark energy could carry signatures of the processes that forged them. Are there subtle, large-scale patterns in the distribution of galaxies that only a cyclic model can explain? Does the measured value of dark energy's strength point to it being a frozen relic of an inflationary field? Each observation we make of the dark universe is, in a very real sense, an archaeological dig into the first moments of existence. These shadows we chase in the present may be the most tangible clues we will ever have to what happened before the dawn of our time, making the invisible architecture of our cosmos the ultimate historical document. But all these scientific visions, from bouncing universes to quantum births, rest on a foundation we have not yet examined, the very framework of our question. We have been chasing the moment before the beginning, but what if the idea of a before is the ultimate illusion? This is not just a physics puzzle, it is a philosophical chasm that forces us to confront the nature of reality itself. For centuries, philosophers have wrestled with the chain of cause and effect. Aristotle argued that everything that happens must be set in motion by something else, a concept that leads inexorably backward to an uncaused first cause, a prime mover that began the entire sequence. This logic feels intuitive. Every event in our daily lives has a preceding cause. A falling domino was struck by another, a lit match was struck by a hand. So it seems natural to extend that chain to the cosmos and demand what struck the first domino, what hand lit the cosmic match. But this reasoning assumes that time is an infinite, pre-existing stage upon which events unfold. What if the stage itself was part of the performance? If our best physics is correct and time itself began with the Big Bang, then the entire concept of before undergoes a radical shift. In our everyday experience, before refers to an earlier point on a timeline that already exists. But if the timeline has a starting point, then asking what happened before that point is like asking what is north of the North Pole. The words form a grammatically correct question, but the question references a direction that ceases to exist at that location. There is no north of the North Pole, only south. Similarly, if time began at the Big Bang, there is no temporal before for anything to exist in. The question what came before may be linguistically sensible but physically and philosophically meaningless. This does not make the mystery vanish, it transforms it. We are no longer searching for an earlier event in time, but for a logical or metaphysical reason for time's very existence. Could the universe be its own cause, a self-contained loop of explanation where the question of a prior cause simply does not apply? Some philosophers and physicists suggest that in a quantum framework, the universe could simply pop into existence without a cause, because at that fundamental scale, the strict chain of causality we know dissolves into probability. The universe would not need a cause because the framework requiring causes did not yet exist. This is a profoundly difficult idea to sit with. It challenges the deepest wiring of our brains, which are built to find reasons for things. Yet it forces a humbling and awe-inspiring perspective. Our search for what came before may be a beautiful, necessary, but ultimately human projection of a narrative onto a reality where narrative, as we understand it, has no purchase. The answer might not be a hidden era or a prior universe, but a quiet revelation that some questions, when pushed to the absolute edge, change their very shape and lead us not to an answer, but to a deeper understanding of the question itself. This relentless questioning of cause and time pushes us toward an even more fundamental possibility. Perhaps our entire universe is not a physical thing that was created, but a timeless truth that simply is. This is the mathematical universe hypothesis proposed by physicist Max Tegmark, and it is a perspective that dissolves the mystery of origin into the quiet certainty of abstract existence. Tegmark's radical proposition is this: our physical reality is not merely described by mathematics, it is mathematics. Every particle, every force, every ripple of space-time is not just modeled by equations, it is the physical manifestation of an abstract mathematical structure. Think of it this way: a perfect circle, as defined in geometry, has no physical substance. It exists as a set of relationships, points equidistant from a center. That mathematical object is eternal and unchanging, regardless of whether anyone draws it in the sand. Tegmark suggests our cosmos is akin to that perfect circle, but of unimaginable complexity. It is a vast, self-consistent mathematical object, and what we experience as the physical universe with its stars and planets is that object's only possible instantiation. In this view, the Big Bang is not an event that happened in time. It is a feature within the structure, a point where certain mathematical parameters take on specific values. The entire cosmic history, from that dense state to the present and into the far future, is simply the unfolding of this mathematical truth, like reading a story from the first page to the last. There is no external creator, no prior physics, because the mathematics itself is the ultimate and only reality. This leads to a profoundly Platonic perspective. Over 2,000 years ago, the philosopher Plato argued that the tangible world we see is a shadow of a higher realm of perfect, eternal forms, like the ideal form of a tree behind every imperfect physical tree. Tegmark's hypothesis updates this for the cosmos. Our universe of matter and energy is the shadow cast by an eternal, unchanging mathematical form. So what does this mean for our central question? The mathematical universe hypothesis suggests the idea of a temporal before is a human construct, a story we impose because we are trapped within the narrative of time, which is itself just one parameter within the grand equation. Asking what came before the Big Bang is like reading a novel and asking what happened before page 1. The story exists as a complete whole. The characters within it experience a sequence of events, but the book itself, the mathematical structure, exists outside of that sequence. It was never created, it just is. In this timeless realm of mathematical truth, universes that can exist do exist. Our particular cosmos, with its specific laws, is simply one of the many possible self-consistent mathematical structures that have actuality. This idea is both incredibly elegant and deeply unsettling. It offers a clean answer to the puzzle of origin. There is no origin, only eternal existence in an abstract sense. But it also places our rich sensory reality, the warmth of sunlight and the vastness of the night sky, on the same fundamental level as a page of symbols in a cosmic textbook. We are not just living in a universe described by math, we are living inside the math. And if that is true, then every mystery we have explored, from quantum bounces to holographic projections, may simply be different ways of glimpsing the same beautiful, silent, and eternal equation. From the silent certainty of mathematical existence, we arrive at a proposition that is both modern and deeply unsettling. This is the simulation hypothesis, a thought experiment that reframes our entire cosmic history as something profoundly artificial. What if our universe, with all its galaxies, black holes, and conscious minds, is not a fundamental reality, but an elaborate simulation, a cosmic video game running on some unfathomable computer in a higher-level reality? In this provocative view, the Big Bang is not a physical event but a logical one. It is the moment the simulation's core code was initialized, the boot-up sequence for a reality engine of staggering complexity. The hot, dense state of the early universe would not be a primordial condition, but a necessary starting parameter, the first frame rendered after the simulation's run command was executed. This transforms the mystery of what came before into a question of infrastructure. The before would be the base reality of the simulators, a universe or civilization operating under its own, perhaps very different physical laws. Our entire cosmos, from the quantum flutter of particles to the majestic spin of galaxies, would be a grand computation, a narrative generated by underlying algorithms. The laws of physics we have painstakingly discovered would not be fundamental truths, but the programmed rules of the simulation, the source code of our existence. This idea gained serious traction in the early 2000s when philosopher Nick Bostrom framed it as a probabilistic argument. He suggested that if any advanced civilization could reach a level of technological maturity capable of running vast, realistic simulations of conscious beings, and if they had any desire to do so, then the number of simulated minds would vastly outnumber the minds in the original, base reality. Statistically, he argued, we are more likely to be among the simulated beings than the original ones. It is a cosmic version of the odds being stacked against you from the very start. The philosophical implications are dizzying. If we are in a simulation, then concepts of free will, destiny, and the nature of consciousness are thrown into question. Are our choices our own, or are they the output of deterministic code? Is the beauty of a sunset a genuine sensory experience, or just a supremely convincing data stream? The search for a unified theory of physics becomes the search for the elegant, underlying programming language. Even the glitches we cannot explain, like the bizarre results of quantum entanglement, might not be mysteries of nature, but artifacts of the simulation, shortcuts in the rendering process to conserve computational power. But can this ever be more than a fascinating speculation? For an idea to be scientific, it must be testable. It must make predictions that can be proven false. Some researchers have proposed looking for potential signatures of a simulated reality. One suggestion is to search for anomalies in the fabric of space-time at the very smallest scales. Just as a digital image breaks down into pixels when you zoom in far enough, our smooth, continuous space-time might reveal a fundamental granularity, a pixelation of reality at the Planck scale. Another clue could be found in the fundamental constants of nature. In a simulation, these constants might be rounded-off numbers or exhibit patterns that betray their origin as programmed parameters rather than emergent properties of a deeper physics. We might also look for literal constraints in the simulation's processing power. The speed of light could be a limit not of physics but of processing speed, a cosmic frame rate that cannot be exceeded without crashing the system. To date, no such definitive evidence has been found, and many scientists argue the hypothesis is fundamentally unfalsifiable, a modern myth that can explain everything but predicts nothing specific. Yet its power persists. It represents a new kind of origin story for a digital age, one where creation is not an act of divine will or quantum fluctuation, but of engineering. It forces us to confront the nature of reality itself, not by looking back to a beginning in time, but by questioning the very substrate of our existence. Whether a testable theory or an unfalsifiable conjecture, the simulation hypothesis stands as a stark mirror to our technological ambitions and our deepest existential uncertainties. If our universe is a program, then who or what is the programmer, and what is the purpose of the simulation we call home? the search for our origin story may feel like a dive into pure speculation, but our universe has left us a tangible clue, a fossilized whisper from its infancy. This is the cosmic microwave background radiation, the CMB, and it is the oldest light we can see. Imagine it as the afterglow of the Big Bang itself, a snapshot taken when the universe was a mere 380,000 years old. Before that moment, the cosmos was a searing, opaque plasma, too hot for light to travel freely. As it expanded and cooled, atoms finally formed and the universe became transparent. That first burst of light has been traveling ever since, stretched by the expansion of space over billions of years into the faint microwave static that uniformly fills the entire sky. This cosmic backdrop is not just a relic, it is a data-rich map. Its near-perfect uniformity tells us the early universe was incredibly smooth, a key prediction of cosmic inflation. But within that smoothness, there are tiny, vital fluctuations, minute variations in temperature of just 1 part in 100,000. These are the seeds of all cosmic structure, the gravitational blueprints from which every galaxy, star, and planet would eventually grow. For cosmologists, this map is a treasure trove, a direct line to the universe's first moments. Yet, as we read this ancient text with ever more sensitive instruments, we have begun to notice potential anomalies, features that do not quite fit the standard story. One of the most intriguing is the so-called cold spot, a region of the sky significantly cooler than the surrounding average. It is a large, mysterious patch that some analyses suggest is statistically unlikely to have arisen from random quantum fluctuations during inflation alone. This has led to a thrilling possibility. Could this cold spot be a bruise, a cosmic scar from a violent event before our own Big Bang? In the context of eternal inflation and the multiverse, one compelling explanation is that our bubble universe, in its hyper-expanding infancy, might have gently collided with a neighboring bubble universe. The energy released in that collision could have left a distinct circular imprint on the CMB, a cooler region that appears as a blemish on the otherwise uniform sky. Another anomaly lies in the large-scale patterns, or lack thereof, across the map. Some scientists argue the fluctuations appear slightly too uniform on the larger scales, as if a piece of the expected pattern is missing. Could this be a sign of a finite universe with a complex topology, or perhaps an echo of a previous cosmic cycle? In models like conformal cyclic cosmology, where one eon gives rise to the next, information is not perfectly erased. The conformal rescaling might preserve faint, large-scale correlations from the previous universe, subtly suppressing certain patterns in the CMB of the new one. These anomalies are hotly debated, and most researchers caution they could still be statistical flukes or artifacts of how we process the intricate data. But that is precisely the point of the scientific quest. The CMB is not a static monument, it is an active crime scene. Teams of scientists are forensic investigators, meticulously scanning this primordial radiation for any fingerprint, any smudge that cannot be explained by the standard narrative of inflation and a solitary Big Bang. They are building ever more powerful satellites and ground-based telescopes, like the Simons Observatory and the Future Light Bird mission, designed to measure the polarization of this ancient light with unprecedented precision. Within that polarization, they hope to find the faint signature of primordial gravitational waves, ripples from the inflationary epoch itself, which could rule entire classes of theories in or out. They are also developing sophisticated algorithms to scour the CMB's temperature map for any non-random features, any shapes or alignments that whisper of a larger, more complex prehistory. This relentless scrutiny transforms our philosophical wonder into an empirical hunt. We are not just dreaming of what came before, we are actively looking for its signature imprinted on the very first light. The cosmic microwave background is our most direct window to the dawn, and every subtle irregularity within it is a potential message, a clue waiting to be decoded. that might finally tell us if our universe has always been alone, or if we are just one chapter in a story far grander than we ever imagined. While the cosmic microwave background is a fossil of light, there is another, more subtle messenger from the dawn of time, one that travels not through the universe, but as a distortion of the universe's very fabric. These are gravitational waves, ripples in space-time itself, predicted by Einstein and first detected a century later from the collisions of black holes. But the most sought-after signals are far older and quieter, the primordial gravitational waves generated in the universe's first violent fraction of a second. If we could detect them, we would be listening to the echoes of creation. The key to this search lies not in the temperature of the cosmic microwave background, but in its polarization, the specific direction in which its light waves vibrate. As this ancient light traveled through the searing plasma of the infant cosmos, it was scattered by electrons, imprinting a specific pattern on its polarization. Most of this pattern, called E-modes, is created by the density fluctuations that seeded galaxies, but a far more elusive signal could be hidden within it, a distinctive swirling pattern known as B-mode polarization. This specific swirl is the unique fingerprint that could only be created by primordial gravitational waves stretching and squeezing space-time as they pass through that primordial plasma. Finding this B-mode signal would be a monumental discovery, a direct snapshot of the universe when it was less than a trillionth of a second old. For many cosmologists, it would be the smoking gun for cosmic inflation, the rapid expansion that is thought to have magnified quantum fluctuations into the cosmic structures we see. The strength of this signal would even tell us the energy scale of that inflationary event, revealing the physics that powered the universe's explosive growth spurt. But the story could be even richer. Some theories suggest these primordial waves might carry whispers from before our conventional Big Bang. In a bouncing universe model, the violent contraction and rebound would generate a storm of gravitational waves with a characteristic spectrum. In the pre-Big Bang scenario, the long, slow contraction phase could also produce a specific, potentially detectable signature. If the primordial B-modes we eventually find have a specific pattern or frequency that doesn't quite match the simplest models of inflation, it could be a clue that our origin story involves a bounce, a prior phase, or something even more exotic. The hunt for these faintest of cosmic tremors is driving a new generation of observatories to the most remote places on Earth and beyond. Ground-based telescopes like the Simons Observatory in Chile's high Atacama Desert and future projects like CMB-S4 are being built with unprecedented sensitivity. Their instruments cooled to a fraction of a degree above absolute zero to detect the minuscule temperature variations caused by these waves. Space-based missions such as the proposed Lightbird satellite aim to fly above Earth's atmosphere to scan the entire sky with pristine clarity, free from atmospheric interference. These endeavors are not merely technical marvels, they are time machines. They are attempting to tune into a frequency that has been ringing through the expanding cosmos for 13.8 billion years, a vibration so faint it is buried under the emissions of galaxies, dust, and even our own atmosphere. To find it would be to touch the instant of Genesis, to move from inferring our history from its aftermath to hearing the first notes of the cosmic symphony as they were played. It is a search for the deepest possible memory of the universe, etched not in light but in the curvature of space itself. These whispers from the cosmic dawn lead us to a deeper, more persistent puzzle. Why did our universe begin in such a perfectly hospitable state? This is not just a question of what came before, but a question of why the starting conditions were so incredibly, improbably right. Think of the Big Bang's initial state as a cosmic hand of cards, dealt from a deck containing every possible configuration of matter, energy, and the laws of physics. To create a universe that lasts billions of years, that forms galaxies, stars, planets, and ultimately life, the hand you are dealt must be extraordinarily specific. It requires a delicate balance and exquisite fine-tuning. Two features are absolutely critical. First, the early universe had an incredibly low entropy. Entropy is a measure of disorder, and a state of low entropy is highly ordered, like a pristine, unshuffled deck of cards arranged perfectly by suit and number. Our cosmos began in just such an ordered, low-entropy state, a smooth, uniform soup of particles. This is what allowed the universe to evolve in a coherent direction, for gravity to gradually pull matter into complex structures over eons, rather than immediately collapsing into maximum disorder. Second, the universe was almost perfectly uniform. The temperature of the cosmic microwave background is the same in every direction to within a tiny fraction of a degree. This smoothness was essential because if the initial explosion had been too lumpy, matter would have quickly clumped into giant black holes, leaving no room for galaxies. If it had been too smooth, matter might never have clumped at all, and stars would never have ignited. So why did we get this perfect Goldilocks hand? The sheer improbability of it forces us to consider that the answer might lie in what happened before our cosmic clock started ticking. Each of the pre-Big Bang theories we have explored offers a different explanation for this fine-tuning, a different reason why the deck was stacked in our favor. In a cyclic universe model, the answer is one of cosmic erosion. The previous universe, through its long evolution and eventual collapse, might have been worn smooth. Any major irregularities, any high-entropy chaos, could have been stretched out and diluted during the contraction phase or erased in the fiery transformation of the bounce. The Big Bang, in this view, is not a random beginning but a reset, a natural recurrence that tends toward simplicity and order, giving each new cycle a clean, low-entropy slate from which to build again. It is as if each cosmic winter freezes the landscape flat, so the spring can begin anew on level ground. The theory of eternal inflation approaches the puzzle from a completely different angle, one of sheer mind-numbing statistics. In an eternally inflating multiverse, every possible initial condition, every possible set of physical laws, is realized in some bubble universe. The vast, overwhelming majority of these bubbles are sterile, chaotic, or stillborn. They inflate into empty voids or instantly collapse or have laws that prevent atoms from ever forming. Our universe, with its specific low entropy and uniform conditions, is not special because it was designed to be that way. It is simply one of the extremely rare bubbles where the random quantum fluctuation happened to produce conditions compatible with complexity and life. We find ourselves here because, well, we could not find ourselves anywhere else. This is the anthropic principle in action, a cosmic version of a puddle marveling at how perfectly the hole it sits in fits its shape. Quantum origins, like the no-boundary proposal, suggest a third kind of answer. Perhaps the specific, smooth state of the early universe was not an accident or a reset, but the most natural, probable outcome from a realm without time. In the fuzzy quantum geometry of the beginning, a smooth, low-entropy configuration might simply have the highest probability of appearing. The universe emerged not from a singular point of infinite chaos, but from a quantum state that inherently favored uniformity and order. It would be like shaking a box of puzzle pieces and finding they have a natural tendency to fall into a nearly complete picture rather than a random jumble. Ultimately, the quest to understand what came before the Big Bang is inextricably linked to this mystery of fine-tuning. We are not just searching for a prior event in a chain of causality. We are searching for a reason why our story had such a promising first page. Did a previous cosmos die to give ours a clean start? Are we a statistical fluke in an infinite multiverse? Or did the universe emerge from a quantum state that inherently leans toward beauty and structure? The answer determines whether our existence is a breathtakingly rare accident, an inevitable recurrence, or the silent preference of reality itself. But if our universe is a bubble or a simulation, what is the canvas it's painted on? Another breathtaking possibility suggests that canvas is not empty space but a dynamic, higher-dimensional arena, and our Big Bang was a shattering impact. This is brain cosmology, a vision born from string theory and its more comprehensive successor, M-theory. To grasp this, we must first stretch our imagination beyond the familiar three dimensions. In this framework, the fundamental objects are not just one-dimensional strings, but higher-dimensional membranes, or branes for short. These can have various dimensions, like two-dimensional sheets or three-dimensional volumes. Our entire observable cosmos, with its three spatial dimensions, could be one such three-brane, a vast, floating island of reality, but it does not float in nothing. It exists within a higher dimensional space called the bulk, which has more dimensions than our brain can perceive. We are like characters living on the flat surface of a page in a massive book, completely unaware of the other pages above and below us or the thickness of the book itself. Now imagine another page, another three-brane, floating parallel to ours in this bulk. According to the ekpyrotic universe model, our Big Bang was not an explosion from a point, but a cataclysmic collision between our brain and that neighboring one. In the before of this scenario, the two branes are separate, slowly moving through the bulk, perhaps drawn together by a force akin to gravity. They approach and finally they strike. The immense kinetic energy of that collision, concentrated along the entire three-dimensional surface of contact, is converted into an unimaginable firestorm of particles and radiation. That moment of impact is our hot Big Bang. The universe did not begin with a singularity in our three dimensions, but with a transformative event in a higher dimensional world. After the collision, the branes bounce apart, soaked in the heat and matter created by the crash. They then slowly drift apart, cool, and the universe on each brane evolves much like our own, with galaxies forming from the debris of the collision. Eventually, the attraction pulls them back together, leading to another collision, another Big Bang, in a potentially endless cycle. This model provides a powerful alternative to cosmic inflation for explaining the smoothness of our universe. The long, slow approach of the branes before the collision acts as a natural smoothing mechanism. Any wrinkles or irregularities on the brane surfaces are stretched and flattened during this gentle approach, ensuring the resulting bang starts from a remarkably uniform state. It also redefines the idea of before in a spectacular way. Before our cosmic dawn, there was no empty void. There was a dynamic, higher-dimensional landscape filled with moving, parallel universes, like great ships in a hidden sea, on a trajectory that would inevitably bring them together in a fiery rebirth. The question of our origin is no longer about a lonely point in nothingness, but about the relationship between neighboring worlds in a reality far larger than we can see. Yet from the canvas of branes and collisions, we can ask an even more radical question. What if the canvas itself emerged from a deeper nothingness, not as a collision, but as a spontaneous shiver in the void? This is the idea of vacuum genesis, a universe born from a quantum fluctuation of nothing at all. To understand this, we must first redefine our idea of nothing. In everyday life, nothing means empty space, a perfect void. But in quantum physics, even the most perfect vacuum you can imagine is not truly empty. It is a vibrant, seething arena, alive with potential. This is due to the Heisenberg uncertainty principle, which states at the quantum scale, you cannot precisely know both the energy of a system and the time over which you measure it. This allows for a bizarre but well-established phenomenon. Pairs of virtual particles, a particle and its antiparticle, can spontaneously pop into existence, borrowing energy from the vacuum itself, only to annihilate each other and vanish back into the void an instant later. This quantum froth is not theoretical speculation. Its effects are measured every day in laboratories, subtly shifting the energy levels of atoms in a process called the Casimir effect. So the quantum vacuum is not a barren stillness, it is a bubbling soup of fleeting existence, a nothing that is profoundly something. The vacuum genesis proposal takes this quantum weirdness to its ultimate extreme. Could our entire universe be one such fluctuation, but on a cosmic scale, instead of a particle-antiparticle pair flickering for a vanishingly small fraction of a second? Imagine a fluctuation so vast it contained the seeds of all space, time, matter, and energy. In this view, the Big Bang is the moment this colossal quantum bubble of spacetime nucleated and critically stabilized. Normally, these virtual fluctuations vanish almost instantly, paying back their borrowed energy. But through a mechanism like cosmic inflation, this one fluctuation could have been stretched and locked into place, its energy converted into the permanent matter and radiation of our cosmos. The universe would then be the ultimate free lunch, appearing from nowhere, with its total positive energy of matter perfectly balanced by the negative gravitational energy of its own curvature, summing to zero. It emerged not from a prior physical state, but as a statistical possibility inherent in the fabric of reality at its most fundamental level. The profound challenge, of course, is defining the nothing that fluctuated. In this model, it is not empty space because space itself was created. It is the quantum vacuum of a more fundamental field, a realm of pure potential governed by the laws of quantum mechanics, existing without a container of space or time. This nothing is a state of zero particles, but not zero physics. It is the arena of quantum fields in their ground state, waiting for a chance event to tip them into something spectacular. While this idea elegantly sidesteps the need for a prior cause or a pre-existing universe, it leaves us with a haunting metaphysical puzzle. If the universe is a quantum fluctuation, what is it fluctuating in? What are the laws that govern that primordial quantum realm, and where did they come from? The vacuum genesis transforms our search from a hunt for a prior event into a contemplation of eternal law, suggesting that the potential for existence might simply be a permanent, uncaused feature of reality, and we are the magnificent accident that potential eventually realized. That quantum froth of potential leads us to a mystery woven into our very consciousness. We remember yesterday, but not tomorrow. A broken glass shatters, but its pieces never leap back together to reform on the table. This relentless forward march, this arrow of time, is the most familiar experience we have, yet its origin is one of cosmology's deepest puzzles. Why does time have a direction at all? The astonishing answer points directly back to the Big Bang's most delicate feature, its incredibly low entropy. Entropy, the measure of disorder in a system, always increases over time, a principle known as the second law of thermodynamics. It is why your room gets messy if you do not clean it, why ice melts in your drink, and why we age. This increase in entropy gives time its arrow, its one-way street. We remember the past because it was a state of lower entropy, and the future will be a state of higher entropy. Our brains and all recording devices work by creating order, which requires a low entropy environment to draw from. So the ultimate source of time's arrow is not in the laws of physics themselves, which are mostly symmetric, but in the specific initial condition of our universe. The Big Bang gave us a universe in a spectacularly ordered, low-entropy state, a wound-up spring that has been unwinding ever since, driving the formation of galaxies, the burning of stars, and the flow of life itself. Without that pristine starting point, time as we know it would have no consistent direction. This realization forces a staggering question about any pre-Big Bang reality. If our arrow of time is a consequence of our low-entropy beginning, what about the state that came before? Did time flow in the opposite direction there? Imagine a universe contracting toward a big crunch. From our perspective, that cosmos would seem to be running backwards, with entropy decreasing as it approached its dense end state. To a being within that universe, however, their experience of cause and effect would feel just as normal as ours. They would remember their past, which would be our future, and anticipate their future, our past. Their arrow of time would point the other way, Or perhaps the pre-bang state was timeless, a realm of perfect equilibrium where entropy was maximized and nothing could happen. No stories could be told because there was no gradient to drive change. Some cosmologists, like Sean Carroll, propose an even more mind-bending architecture. He suggests our universe might be two-headed, with a big bang not only in our past but also in our far, far future. In this vision, the low-entropy Big Bang is not a unique beginning but a central point of symmetry. On one side, time flows forward as we experience it, with entropy increasing toward a vast, empty future. On the other side, another timeline stretches out, mirroring our own, where entropy also increases away from that central point. From the perspective of that mirrored realm, their Big Bang is in their past, and our long, cold future is their deep past. In this model, the arrow of time is not a universal absolute, but a local phenomenon, a direction we perceive because we are on one particular slope of a grand cosmic hill. The summit of that hill, the point of lowest entropy, is the Big Bang itself. We are forever sliding down one side, unable to see the other slope where time, from our vantage, appears to run in reverse. This elegant idea transforms the beginning from a solitary gate into a symmetrical peak, a moment of such exquisite order that it gives direction to time in two distinct cosmic epochs. It suggests that what we call the past and the future might be more similar than we ever dreamed, both unfolding away from a single, silent, and perfectly ordered moment of Genesis. This profound elegance, however, confronts a stark and humbling reality. For all their mathematical beauty and logical coherence, these theories of cosmic origins share a monumental challenge. How can we ever truly know which, if any, is correct? The quest to peer before the Big Bang pushes us to the very edge of scientific inquiry, where the line between profound physics and pure metaphysics becomes dangerously thin. The core of the scientific method is testability. A good theory must make specific, concrete predictions that can be checked against observations or experiments. If those predictions fail, the theory is falsified and we move on. This ruthless process of elimination is what separates science from speculation. But when we ask about the state of reality before time and space as we know them began, we are asking a question that, by its very nature, seems to resist this process. Many of the ideas we have explored, from the string landscape to the holographic principle, are currently untestable. They exist as breathtaking mathematical narratives, but they make predictions about phenomena that occurred at energy scales 1 trillion times beyond what our most powerful particle colliders can recreate. Or they describe realms that are, by definition, outside our observable universe. For instance, the idea of a cyclic universe where one eon conformally rescales into the next is a compelling story. But what definitive, observable signature would prove it happened? The potential cold spot in the cosmic microwave background is intriguing, but it could also be a statistical fluke. The detection of primordial gravitational waves would be a triumph, but even their specific pattern might be interpreted in multiple ways, supporting different models of inflation rather than a clear pre-Big Bang scenario. This is the great tension at the heart of cosmology. We have brilliant minds constructing castles in the sky of mathematics, but we lack the ladder to climb up and see if they are actually there. Some critics argue that without a path to falsification, these ideas drift into the realm of philosophy or even mythology, beautiful stories that explain everything but predict nothing unique we can go out and find. This is not a failure of imagination, but a reflection of the staggering difficulty of the problem. We are trying to reconstruct a crime scene where the crime created not just the victim, but the entire continent, the laws of physics, and the very concept of evidence itself. The struggle, then, is to find those elusive fingerprints. Scientists are not giving up. They are searching for any indirect signature, any subtle anomaly in the data we can collect. They scrutinize the cosmic microwave background for patterns that no standard inflation model can produce. They calculate the precise gravitational wave signatures that a bounce or a brain collision would leave, hoping our future detectors are sensitive enough to find them. They explore whether the fundamental constants of nature might vary in ways that hint at a larger multiverse. This is slow, painstaking, and often frustrating work. It requires a blend of audacious creativity and rigid skepticism, a willingness to dream grandly about the cosmos while demanding that those dreams eventually touch down on the solid ground of empirical data. This honest appraisal does not diminish the quest, it elevates it. It shows science at its most ambitious and its most humble, wrestling with the ultimate questions, fully aware that the answers may lie forever beyond our grasp, yet driven to reach for them anyway. The search for what came before is not just a hunt for an answer. It is a testament to our need to understand, to trace the chain of existence as far back as logic and curiosity can possibly take us, even if that journey leads us to a silent wall at the edge of reality. This honest tension between imagination and evidence is precisely what drives the next great leap in our quest. We are building new eyes and ears for the cosmos, instruments of such breathtaking sensitivity they might finally turn these grand philosophical stories into hard, testable data. The next decade promises a revolution in observational power, with a fleet of new observatories designed to probe the universe's first fractions of a second. Leading the charge in space is the Nancy Grace Roman Space Telescope. Scheduled to launch in the late 2020s, Roman is not just another deep-field telescope. Its core mission is to conduct a monumental survey of billions of galaxies, mapping the cosmos's large-scale structure with unprecedented precision. But how does a galaxy survey tell us about the Big Bang? The answer lies in the subtle tug of dark energy and the faint imprint of primordial sound waves. By measuring how the distribution of galaxies has changed over cosmic time, Roman will put the most stringent constraints yet on the nature of dark energy. Is it truly a cosmological constant, a steady energy of the vacuum, or does its strength change over time? That distinction is crucial. If dark energy's strength varies, it could be a clue that it is a dynamic field, perhaps a relic of the inflationary epoch itself, slowly fading or evolving since the dawn of time. Furthermore, by charting the vast cosmic web in exquisite detail, Roman could find statistical anomalies in the pattern, large-scale correlations or asymmetries that the standard model of inflation cannot easily explain. Such a discovery might point to a more complex origin, perhaps a pre-existing geometry or a collision event from before our bubble universe formed. On the ground, the hunt for the universe's first light is entering a new golden age. In the thin, dry air of the Chilean Andes, the Simons Observatory is nearing completion, and the even more ambitious CMBS-4 project is in advanced planning. These are not single telescopes, but arrays of hundreds of thousands of ultrasensitive detectors, chilled to a fraction of a degree above absolute zero. Their singular goal is to read the cosmic microwave background like never before, searching for that elusive swirling pattern in its polarization, the B modes that are the signature of primordial gravitational waves. Finding this signal would be like hearing the faint echo of the universe's first vibration. Its strength would tell us the energy scale of inflation, revealing the physics that powered the universe's explosive growth. But even more tantalizing, the detailed pattern of those B modes could hold surprises. If the signal shows specific frequencies or correlations that don't match simple inflation models, it could be evidence for a bounce, a prior contracting phase, or even the collision of cosmic brains in a higher dimensional bulk. These experiments are so sensitive they might detect not just the waves from inflation, but any gravitational ruckus from the very first instant of classical time, offering a direct audio recording of creation's opening chord. While some listen for the echoes of space-time's birth, others are preparing to sense its quietest ripples from space itself. The Laser Interferometer Space Antenna, or LISA, is a revolutionary mission led by the European Space Agency with NASA participation. Imagine 3 spacecraft flying in a perfect triangular formation millions of kilometers apart, connected by lasers. This will be the first dedicated gravitational wave observatory in space, and its sensitivity is almost beyond comprehension. LISA will detect waves at frequencies far lower than any ground-based detector can, opening a window onto the mergers of supermassive black holes and the subtle chirps of white dwarf binaries. But for our origin story, its potential is even more profound. LISA could detect a stochastic gravitational wave background, a permanent hum of ripples from the very early universe. This hum could be the combined roar of countless cosmic string loops, hypothetical one-dimensional defects that might have formed during a phase transition in the universe's first moments. Their detection would be a direct probe of physics at energies a trillion times higher than any collider can reach. Furthermore, some models of pre-Big Bang scenarios or certain string theory cosmologies predict a very specific spectrum of this gravitational wave hum. If LISA's data matches one of these exotic predictions, it would provide compelling evidence that our universe underwent a dramatic transformation, a bounce or a collision, rather than a simple expansion from a singular point. And what of the energy scales themselves? To understand the furnace of the Big Bang, we must recreate in miniature the conditions that existed. This is the domain of particle colliders like the Large Hadron Collider and its potential successors. While no machine on Earth can ever reach the Planck energy of the universe's birth, they can probe the physics of symmetry breaking and phase transitions. By smashing particles together at nearly the speed of light, we recreate for a fleeting instant a speck of the universe as it was a trillionth of a second old. Future colliders with higher energies and intensities could discover new particles or forces that were prevalent in that primordial soup. Finding evidence for supersymmetry, for example, would provide strong support for string theory and its vision of a multiverse landscape. More speculatively, if certain stable, exotic particles are created in these collisions, particles that match the predicted properties of dark matter, we might be holding in our detectors a relic that has existed since the first instant. Studying its properties would be like performing an archaeological dig on the moment of creation itself. Each of these tools, from the wide-eyed galaxy surveys of Roman to the hypersensitive listening posts of LISA and the subterranean cosmic fireplaces of particle colliders, represents a different strand of inquiry, a different way of interrogating the past. They may not give us a photograph of what came before, but they can provide the forensic evidence, the fingerprints and the DNA that will allow us to reconstruct the crime scene of existence. The philosophical dreams of today are slowly, painstakingly, being wired into the circuits of tomorrow's experiments, turning our wonder into a waiting signal, a data point on a graph that could change everything we think we know about our own beginning. Long before telescopes and equations, humanity looked up at the star-filled sky and told stories. Every culture in every corner of the globe crafted narratives to explain the awesome mystery of existence. These are the creation myths, the ancient and enduring attempts to answer the very question we are still asking today. From the cosmic egg of Hindu and Chinese traditions to the emergent stories of indigenous peoples where the world is sung or woven into being, from the Babylonian epic where order is carved from a chaotic sea to the philosophical doctrine of creatio ex nihilo, creation from nothing, found in Judeo-Christian Islamic thought, these narratives share a profound common thread. They are not primitive science but foundational poetry, addressing the deep human need for meaning, purpose, and a place in the cosmos. They sought to establish not just a physical origin, but a moral and spiritual order, connecting the birth of the universe to the values and lives of the people who told the tales. The scientific quest we have been exploring operates in a different realm, one of testable hypotheses, mathematical models, and empirical evidence. It deliberately sets aside questions of purpose or divine intent to focus on the mechanisms of how. Yet to see these as conflicting narratives is to miss a grander, more unifying truth. Both the ancient mythmaker gazing at the campfire and the modern cosmologist analyzing data from a satellite are driven by the same irreducible human impulse, wonder. That feeling of awe in the face of the vast and unknown is our shared inheritance. It is what compels us to ask why we are here, to trace our lineage back to the first moment, whether that moment is described as a divine word, a giant's body, or a quantum fluctuation in a higher dimensional bulk. This universal drive connects us across millennia. It reminds us that the search for origins is not a cold, academic exercise, but a deeply human one, a story we have been telling ourselves about ourselves since the dawn of consciousness. Our tools have evolved from oral tradition to supercomputers, but the fundamental question and the awe that fuels it remains beautifully, powerfully the same. The landscape of cosmic origins is not a barren plain with one lonely monument, but a vibrant, sprawling city of ideas. We have wandered its districts from the rhythmic avenues of cyclic universes to the bubbling quantum neighborhoods of spontaneous creation, from the towering skyscrapers of the multiverse to the quiet, timeless gardens of mathematical reality. Each theory is a masterpiece of human imagination and logic, a different colored tile in a grand, unfinished mosaic. Look at them side by side. The cyclic model offers eternity, a universe with no true beginning or end, forever breathing in and out. Eternal inflation offers infinity, an endless foam of universes, each with its own unique laws. The holographic principle redefines reality itself, suggesting our three-dimensional world is a magnificent projection. Quantum origins like the no-boundary proposal erase the starting line entirely, presenting a cosmos that is finite yet unbounded. And woven through them all are the haunting clues of dark energy, the arrow of time, and the pristine order of the cosmic microwave background. This dazzling diversity is not a sign of confusion, but of profound exploration. These ideas are not necessarily mutually exclusive, battling for a single crown. They are different perspectives, different languages attempting to describe the indescribable. Think of them as maps of the same unknown territory, one drawn by a cartographer, another by a poet, and a third by a musician. The cyclic bounce could be the mechanism within one bubble of an eternally inflating multiverse. The holographic projection could be how information is processed across the boundary from one eon to the next in a conformal cycle. The mathematical universe could be the timeless substrate from which all these dynamic processes emerge. The true answer, if we ever find it, will likely be a synthesis, a grand unified vision that borrows elements from several of these stories, weaving them into a coherent theory of everything that can finally tell us how space, time, and matter came to be. This is the beautiful, humbling state of our quest. We do not yet have the final answer, and we may never have one that is complete and certain. But we have something equally valuable, a map of human curiosity at its most ambitious. We have built these conceptual cathedrals not from stone, but from mathematics and wonder, each one a testament to our relentless drive to understand our place in the cosmos. The search for what came before the Big Bang is more than a scientific puzzle. It is the story of us reaching as far as our minds can possibly go, tracing the light of existence back to its source, and in the process, illuminating the incredible power of the human spirit to ask and to dream. This journey has taken us from a single point of infinite mystery to an entire cosmos of possible beginnings. We began with the stark wall of the singularity, a mathematical dead end where our known physics fails, and we have ventured far beyond it. We explored universes that bounce in eternal cycles, others that bloom as bubbles in an endless inflationary sea. We considered the possibility that our reality is a holographic projection, a mathematical truth, or even a sophisticated simulation. Each theory, from the quantum birth of a no-boundary cosmos to the cataclysmic clash of cosmic brains, represents a monumental leap of human imagination, a desperate and beautiful attempt to answer the unanswerable. The simple question, what came before the Big Bang, has proven to be the ultimate catalyst, not for one answer, but for a revolution in thought. It has forced us to dismantle our most basic assumptions about time, space, and cause and effect, pushing the very frontier of physics to its breaking point and beyond. This is not a sign of failure, but of profound progress. It reveals a universe far stranger, more vast, and more wonderfully mysterious than we ever dared to dream from our small planet. So let this wonder be your compass. Stay curious. Support the scientists and engineers who are building the next generation of telescopes and detectors, listening for the faintest echoes of creation. Their work turns philosophy into data and mystery into understanding. And as you look up at the night sky, carrying all these possibilities in your mind, ask yourself which vision of our cosmic origin resonates most deeply with you. Is it the eternal rhythm of a cyclic universe, the infinite chance of a multiverse, or the elegant self-containment of a quantum beginning? Share your thoughts, join the conversation, and keep that flame of awe burning. For in asking these grand questions, we do more than seek our past. We define our future and celebrate the incredible human journey to comprehend our place in the story of everything.